So talk about the infinite and the infinitesimal concepts that you've researched with, particularly that case study that I read as well.
Oh, okay, yeah.
So what is it? We have the number line. So talk about the number line and what happens there in the very small section of a number line and why that matters.
Okay. Okay, so I'll talk about the infinitesimal first. And this is kind of interesting because it starts with, what I noticed started with asking people, what is 0.9 repeating? And what's between that and 1? And of course, a mathematician will say that 0.9 repeating is 1. Those are equal to each other. But most kids don't think that, and most college students don't think that. They think that 0.9 repeating is really close to 1. How close is it to 1? If you press them on it, they say, well, it's some very, 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 very small distance. Smaller than any other number, but not 0. A lot of times people will say that, and I found students talk about this. So they believe that there are these really small numbers that are smaller than any other numbers, but yet they're not nothing. And in mathematics, we don't believe that these things exist, but historically people have believed these things exist. In fact, this is where calculus comes from. They called it the Infinitesimal Calculus. Both Newton and Leibniz believed that there were infinitesimal quantities smaller than any other number, but still bigger than 0. And what you wanted to do when you were looking at the relationship between two quantities, you found a really, really infinitely small part of one and look at the ratio of that to an infinitely small part of the other, and that gives you some relationship between those two quantities that you wouldn't find if you had to look at a big chunk, a normal size one. So the fact that students think in terms of, or want to think in terms of infinitely small things, even though mathematically now we don't believe that that is correct, that those things exist, it still is a powerful way of reasoning for students. So one thing that we can do is address that conception. Like, where does that come from? Why do people want to believe those things, that those little infinitely small things exist? And what does it do for them cognitively to believe that? So the example that you gave me, I had a student who was able to work with these things. It said, well, 0.9 repeating is really close to 1. How far away is it? Well, it's 0.0 repeating forever with a 1 after it. That's how far away it is. How many zeros are there? Oh, there's infinitely many zeros. Oh, all right. Well, can you find another number that's even closer to 1? Yeah, 0.9 repeating with another 9 after it. Okay, well, what if how close is that? Oh, that's 0.0 repeating with another 0 after it and then a 1. So there's all these little numbers in there. It's almost a little world full of infinitesimal numbers. This is a completely coherent way of viewing what happens on the number line. But it's not the way that we view it now. It's the way that mathematicians like Leibniz 300 years ago viewed it. So it's not irrational, it's not wrong, it's not a misconception, it's a different conception that students have that come out of somewhere.
So now what does the number line look like?
Well, yeah, right now we believe that, of course, there are finite numbers and there's 0. And there are no numbers that are smaller than any finite number. So if you have a number like 0.9 repeating and it's 9s all the way out, there is no distance between that and 1. That is the number 1. It's a different way of writing 1. That's what we believe now. And that's perfectly coherent, but it's not natural to all students to think that way. And we, of course, don't talk about the number line with students very much. We just assume that they will understand it the same way that we do. So if you give people a proof that 0.9 repeating equals 1, and they see the proof and they follow every step of it, they still don't believe it. And it's very interesting.
So,
it doesn't convince them because they have a view of the number line that includes these small infinitesimal distances a lot of times.
Well, maybe cognitive science will teach us something about why we can't perceive maybe infinitely small, infinite anything.
Well, it's all made up, right? An infinitely small thing isn't a real thing in the world. Leibniz called it a useful fiction. It's not real. It's something that we make up in order to do a job for us, in order to fill a hole. Same with infinite things. When we imagine a limit of some process that goes on infinitely far, we imagine what the end result is going to be. We can't do it. We can't do infinitely many steps, but we can imagine it. We can abstract it. And that's what we do all the time. So anything in mathematics and higher mathematics that has infinite things, infinite sets, we're always generalizing to that world that we don't really know anything about, but we invent in order to because it has to be that way in order to be coherent. So we invent these infinite things, and then we can work with them perfectly happily. You can't point out an infinite set in the real world, but that doesn't stop us. Why should it?
Okay, now I want to pull back a little bit and talk about sort of the value of mathematics. Clearly, there's a very functional part of why math is valuable in the world. Engineers use it, computer science, it's just all over as a tool. But I do every once in a while run into a person who's really good at math, or was, and decided to leave the field because, as I hear it, there wasn't enough meaning in it.
There wasn't enough meaning in it.
Can you address the math doesn't really mean very much to people question?
Well, part of it, I think that you're kind of getting at the question of like, why is math valuable? Why do we even bother teaching it at all? And the standard answer that a lot of people give is that, oh, it's really important, like you all have to learn math because you have to balance your checkbook and you have to do your taxes, and these are important skills. But at the end of the day, it doesn't really hold water. The math that most people use in the world, they would have probably figured out by the time they're in 8th grade. And yet we demand that they learn algebra and all these other things that most people don't use a lot of the time. So you say, okay, fine. Most people aren't going to use that, but what if you're going to be an engineer? Then you need to know it. Well, that's true too, but there's a lot of math that people learn that they're going to be engineers with, or whatever other mathematical field that they're in, they're not going to use in those fields. We learn Euclidean geometry. It isn't really about engineering. It's a world of interesting ideas. So is it meaningful? It's meaningful, but it might not necessarily be meaningful in a way that is going to help you in everyday life. It's meaningful because it's a world of ideas that you can understand and see patterns in and explore, more like a game, right? It's not only a world of ideas that is interesting in and of itself, it's also a world of ideas that people have played with in all different parts of the world for thousands of years, and they have enjoyed and explored, and many of the great ideas that they've come up with have been shown through the mathematical ideas that they've developed. So you can't really understand a culture unless you understand its mathematical ideas, what kind of mathematical things it's exploring and how it talks about those. So I think that that's another way in which math can be meaningful, is as a window into human culture. So I think all of those things are ways in which math can be meaningful for different people. And if you find someone who's not engaged with one, give them a different thing. If you find someone who really wants practical mathematical ideas, give them those things. If you want someone who wants a world to explore and play in that doesn't have to describe the real world, math does that too. And that can be where a lot of people find meaning.
But why wouldn't math describe the real world?
Well, sometimes
at all?
It's not that it doesn't at all. It's that some mathematical ideas are explored not in order to describe the real world, but in order to, I mean, maybe they came originally from trying to describe the real world or what people's experiential reality is. But then they were abstracted, and now we're playing with these ideas and just seeing what happens with them. So long, long ago, maybe they had some real world application or real world descriptive power, and now they don't. But that doesn't stop us, because we say, oh, what happens then? What happens with the infinite sets? It doesn't describe the real world, but it's really interesting. But you can't be tied to math's descriptive power as its reason for existence, because that limits the world of math that you look at. And it's not as much fun sometimes.